Hello, let us talk about the pressure volume diagrams in thermodynamics. Pressure volume diagrams are of immense importance in thermodynamics. মানে চাপ আর তাপের যে ডায়াগ্রামটা যে গ্রাফটা সেটা থার্মোডাইনামিক্সে খুব ইম্পর্ট্যান্ট রোল প্লে করে। কি ইম্পর্ট্যান্ট রোল প্লে করে সেটা আমরা একটু অ্যানালাইজ করব এবার। But before going to that, we would like to recall you the first law of thermodynamics, which states that the change in the internal energy, which is equal to delta U, is sum of the heat supplied to the system plus the amount of work done to the system. These are some sign conventions which states that if the system gets heat, that is heat is entering into the system, then Q is positive. And if heat is extracted from the system, মানে তাপ যদি শোষণ করে নেওয়া হয় সিস্টেম থেকে, then Q becomes negative. Similarly, if work is done on the system, then W is positive, and if work is done by the system, then W is negative. সিস্টেম যদি নিজে কাজ করে তাহলে W is negative, আর সিস্টেমের ওপরে যদি কৃতকার্য করা হয় then W is positive. These are the sign conventions. This is the famous heat steam engine. We are well aware about it. Steam engine, James Watt. Steam engine এর প্রিন্সিপালটা হচ্ছে there is a certain amount of water is inside the engine which expands by taking a certain amount of heat, and because of the expansion the steam is able to propel the locomotive. Steam বা বাষ্পের প্রসারণ ঘটানো হয়, বাষ্পটিকে কিছু পরিমাণে তাপ দেওয়ার পরে স্টিম বা বাষ্পটির প্রসারণ ঘটে এবং এই প্রসারণের সময় যে কৃতকার্য সেটা দরুন স্টিমটা লোকোমোটিভ বা ইঞ্জিনটাকে পুল করে নিয়ে যেতে পারে। Now these are some thermodynamic variables. Before going into discuss the PV diagram is actually the relationship between pressure and volume. I mean, with the change in volume, how the pressure changes. So these are some relations between pressure and volumes. We here define only a number of thermodynamic quantities, thermodynamic coordinates, which is pressure, volume, temperature. And if these two things are defined, suppose in this relation temperature and volume is defined, so we can find out the pressure. In this relation temperature and pressure is defined, so we can find out the volume. Similarly, in this case pressure and volume both are defined and we can find out the temperature, where this is a constant small n, this denotes the number of moles, মানে মোলের সংখ্যা। Capital R is the molar gas constant, এটা হচ্ছে এমন একটা ধ্রুবক যেটা which is actually serves as per mole. Let's discuss about some functions, which is first we will discuss about state functions, then we will discuss about path functions. Thermodynamics এর তাপগতিবিদ্যার কিছু অপেক্ষকের কথা এবার আমরা আলোচনা করব। First we would like to discuss about state functions. State functions are those functions in thermodynamics whose value depends only on the particular state of the system on which the system is residing now. It does not depend on the path of reaching that particular state. That is, state function হচ্ছে এমন একটা ফাংশন যেটা সিস্টেমের তখনকার অবস্থার উপরেই শুধুমাত্র ডিপেন্ড করে, সেই অবস্থায় সিস্টেম কিভাবে পৌঁছেছে তার উপরে ডিপেন্ড করে না। ফর এক্সাম্পল, think about mechanics. If we think about potential energy of a person who is doing trekking from bottom of a mountain to the top of a mountain, so its gravitational potential energy is depending on the mass of that particular person multiplied by value of the acceleration of gravity on that particular place into height of the person from the sea level. So, it is m into g into h. So, this value depends only on the position of the person, where the person is residing or standing. It does not depend on how the person has reached that particular position. He may have taken some car, he may have taken some horses, or he may have walked all the way. So, কিভাবে সেই স্টেটে পৌঁছেছে তার উপরে পোটেনশিয়াল এনার্জি, গ্র্যাভিটেশনাল পোটেনশিয়াল এনার্জি বা অভিকর্ষীয় স্থিতিশক্তি কিন্তু নির্ভর করবে না। Similarly, in thermodynamics there are some functions which are called state functions, whose value depend entirely on the state of the function, not on the path of reaching that particular state. And these are the examples of thermodynamic state functions. These are the examples of thermodynamic state functions. For example, it is pressure, volume, temperature, চাপ, আয়তন, তাপমাত্রা, enthalpy, internal energy, Gibbs free energy, entropy. This is enthalpy, এটা আভ্যন্তরীণ শক্তি, Gibbs free energy and the entropy. The value of this state function depend on the current condition of the system, not on the history of the system. For example, if we look into pressure of a substance, suppose we have a certain amount of gas inside a container, and on the top of the container there is a piston. The piston can move up or down, and up and down. Now, we can increase the pressure on the gas by just pressing down the piston, and we can increase the pressure by keeping the same gas of the same amount to another container with a smaller volume. So, in that case, in the second case, the pressure inside the smaller container will be greater than the previous one. So, the pressure here changes, and the amount of change of pressure does not depend on how the pressure is made to change. Suppose আমাদের কাছে এক কন্টেনারের মধ্যে একটা সার্টেন অ্যামাউন্টের গ্যাস আছে, তার প্রেশারের একটা পার্টিকুলার ভলিউম আছে, কন্টেনারের ওপর দিকে একটা পিস্টন লাগানো আছে। পিস্টনটাকে যদি আমি নিচের দিকে মুভ করিয়ে দিই, তাহলে গ্যাসটা আরও কম্প্রেসড হয়ে যাবে, আরও সংকুচিত হয়ে যাবে, গ্যাসের প্রেশারটা বেড়ে যাবে। এবার আমি যদি ওই সেম গ্যাসটাকে নিয়ে আর একটা ছোটো কন্টেনারের মধ্যে, যার আয়তনটা আগের কন্টেনারের থেকে একটু কম, তার মধ্যে যদি রেখে দিই, তাহলে এখন ছোটো কন্টেনারের মধ্যে গ্যাসটা আরও বেশি প্রেশারাইজড হয়ে থাকবে, গ্যাসের ওপরে চাপটা আরও বেশি হবে, কারণ এখানে আয়তনটা কমে যাচ্ছে। হিয়ার দ্য চেঞ্জ অফ প্রেশার, মানে চাপের পরিবর্তনটা নির্ভর করবে only on the initial pressure and the final pressure. কিভাবে প্রেশারের চেঞ্জটা করা হয়েছে, চাপের চেঞ্জটা করা হয়েছে, তার উপরে কিন্তু নির্ভর করবে না। So, there are other types of functions which are known as path function. For example, work and heat, these are the path functions. This depends on the path at which the system arrives at a given state. Now, let us have a look at the path function. We have plotted the PV diagram for a certain amount of gas, say. This is a point 1, this is point 2. For this point 1, this is having a certain value of pressure P1 and certain value of volume V1, and the point 2 is having a value of pressure P2 and value of volume V2. Now, we can go from 1 to 2 via two paths. One is touching D and the other is along this curve, this is through C. The work done, as in mechanics we have seen that work done equal to F multiplied by the distance travelled. Now, F is nothing but pressure into area, so it is PA dl. Now, what is A dot dl? A dot dl is area times the length, so it is giving us the volume change. So, if we see this PV diagram, the volume enclosed under this is certainly different than the volume enclosed under this curve. This is certainly bigger volume, the entire volume is here, entire portion is here. So, if we reach from 1 to 2 via this path and via this path, then of course, the volume change is different. So, work is different. Now, if we want to calculate the amount of work for this and for this, if we reach from 1 to 2 through D and if we reach from 1 to 2 through C, it is quite evident from these two plots, from these two diagrams, that the area covered under this C path and the area covered under the path across D is quite different. So, these two work dones are different. Now, let us calculate the amount of work done in different processes. Suppose we have some isobaric process. Isobaric means pressure is constant, volume and temperature can change. Cooking on an utensils is a good example of an isobaric process, because if the lid is open, or say if it is closed too, if the lid is open for example, then the pressure on the pot is entirely the pressure of the atmosphere. So, the pressure is constant there. So, for isobaric process, pressure is constant, the volume changes from VA to VB. So, volume change here is delta V, which is VB minus VA. So, area under the curve is P is the value of this length, because this is the value of the y axis here and this is the value of the x axis here. So, if we want to calculate the area, so it is this multiplied by this, that is length into breadth, length into breadth. So, area will give me P into del dV, pressure, constant pressure, into change in volume, which will give us the work. Now, for example, for isovolumic process, when the volume is constant, we are not interested about this kind of situation, because here, because as the volume is constant, dV is equal to 0 and work done is by definition P into change in volume, pressure into change in volume. So, as there is no change of volume, so W is equal to 0 here. So, for this kind of process, work done is 0. This is isothermal process. Isothermal process is where the temperature remains constant. For the temperature remains constant process, we have this kind of hyperbolic plot in this PV diagram. Here volume changes from VA to VB, and this point is having a set of value of pressure and volume. This point is having another set of pressure and volume. Here the pressure is less, the volume is greater, but here the pressure is more and the volume is lesser. So, if a system goes from A to B, work done is the area enclosed by this section of the graph. Now, work done is calculated like this. We have F force equal to pressure into area. So, work done W equal to, we know, F dot dx, force into displacement. The force is given by pressure into area. So, pressure into area into dx. So, this way if we integrate this for a certain volume V1 to V2, we will get this. Now, we can't take this P outside the integral, because here P is not constant. As we can see from this plot, P is not constant, here P is decreasing. So, we can't we can't take this P out of this integration. but we can substitute of course the value of P by virtue of ideal gas equation. Ideal gas equation tells us that PV equal to nRT. So, we can put the value of P equal to nRT by V over here, and we can integrate over volume. So, it is just a single variable, that is a volume variable integration will be left. This is a problem, this is to be done by you, the answer is given here. Now, come to an adiabatic process. When a tire bursts, if we can feel the air coming out of the tire, we can feel that the air coming out of the tube is cooler compared to the atmosphere. What happens for the case of tire puncture is an adiabatic process. For adiabatic process, no heat exchange is done between the system and its surrounding. So, dq or q is equal to 0. So, we know from the first law of thermodynamics that del U, that the change in internal energy equal to q plus W. So, q is 0 here. So, we have left with the work done only. So, del U, change in internal energy, is entirely dependent on the work done by the system. Now, let us come to the lecture opening question. We were asked that an expanding steam does some work on the locomotive and it propels the locomotive by the virtue of its expansion. Now, if the steam is contracted, is it possible for the steam to propel the locomotive as well? The answer is no, because if we look into this equation, work done is equal to pressure into change in volume. As the steam gets contracted, স্টিমটা যেহেতু সংকুচিত হচ্ছে, বাষ্প যেহেতু সংকুচিত হচ্ছে, so its volume change is negative, because initially the volume was greater, finally the volume was lesser. So, the volume change is negative here and work done is negative here. So, it is not possible for the steam engine to propel the locomotive when the steam is contracted.